In this video we're going to look at Isaac Newton's first and second laws of motion as well as explore the fundamental concepts of circular motion and inertia. Newton's first law basically tells us that a resultant force is necessary to change the motion of any object, or in simpler terms, if there is no resultant force acting on an object then its motion will remain exactly the same. This principle applies equally to objects that are stationary as well as those that are already in motion. So if the resultant force acting on a stationary object is zero, meaning there is absolutely no net force being applied, then the object will continue to remain stationary without any change in its state. Similarly, if a moving object has no resultant force acting on it, then it will continue moving in the same direction and at the same constant velocity without slowing down or speeding up because no external force is pushing or pulling it. In both these scenarios, the absence of a resultant force ensures that the motion stays unchanged. Moving on to Newton's second law, which provides a contrast to the first, this one states that if there is a non-zero resultant force acting on an object, then it will definitely cause the object to accelerate. Now when we say non-zero, we simply mean any value other than zero, so basically any actual force. For instance, imagine we take a small particle and draw arrows representing unequal or unbalanced forces acting on it in different directions. If the force arrow pointing to the right is larger than the one pointing to the left, then we clearly have a resultant force acting to the right. This imbalance means that the particle will accelerate towards the right. However, depending on the original state of motion of the particle, this rightward acceleration could lead to several different results. For example, if the object was initially stationary, then this acceleration would cause it to start moving in the rightward direction. If the object was already moving to the right, then this additional force would make it move faster, or in other words, increase its speed. On the other hand, if the object had been moving to the left and the force acts to the right, then the acceleration would slow it down since it is working against the motion. If the object was already moving leftward at a slower speed, the rightward acceleration could potentially bring it to a stop. The most subtle and sometimes confusing outcome is when acceleration results in just a change in direction without any change in speed, and this still counts as acceleration. This is because acceleration is technically defined as the change in velocity over time, and velocity itself is a combination of both speed and direction. So even if the speed remains the same, a change in direction means a change in velocity and therefore counts as acceleration. A practical example of this is circular motion, such as the moon orbiting around the Earth. Even though the moon's speed stays consistent throughout its orbit, we still say it is accelerating because its direction is constantly and gradually changing as it moves. This continuous change in direction is due to the gravitational force exerted by the Earth's mass, which pulls the moon perpendicularly to its path of motion. As a result, the moon follows a curved path around the Earth, maintaining a constant speed but an ever-changing direction, which means its velocity is not constant and thus it is accelerating. Another important detail from Newton's second law is that the size of the resultant force is directly proportional to the acceleration it produces. To put it simply, if you double the force, then the acceleration also doubles, assuming the mass stays the same. This relationship is captured in the well-known equation force equals mass times acceleration. For example, let's revisit our earlier particle, which we now say has a mass of 0.25 kilograms and is being pushed by a force of 30 newtons to the left and 42 newtons to the right. To find the resultant force, we subtract 30 from 42, giving us 12 newtons acting towards the right. Using our formula, we rearrange it to get force divided by mass equals acceleration. Plugging in the numbers, we divide 12 newtons by 0.25 kilograms to find the particle's acceleration, which comes out to 48 meters per second squared. Finally, we come to the concept of inertia, which refers to an object's natural resistance to any change in its motion. It's essentially another way of describing Newton's first law, which tells us that unless a net force is applied to an object, it will either remain at rest if it was already still or keep moving at the same velocity if it was already in motion. Inertia is all about that tendency to keep things just the way they are. An object's inertial mass is a way of measuring how much resistance it offers to a change in its velocity, and we can calculate it by dividing force by acceleration, which again is just Newton's second law in another form. So an object with a very large mass like the moon will have a lot of inertia, which means it will need a significantly larger force to make even a small change in its motion, and even then the acceleration will likely be very modest. So that wraps up everything we set out to discuss in this video. If you found it helpful or interesting, be sure to check out some of our other physics videos, and hopefully we will see you again next time.